evening to one and all present here. Hope you're all safe and healthy. On behalf of ISA Bangalore students, I welcome all participants to the second day of the online mathematics camp of limit. Today's student lecture will be given by Rishika Agrawal. She is currently pursuing BMAT honors and is in her third year. Her main topic of interest is number theory, and we are going to hear from her on the topic Gallagher, Sieve, and Diophantine M tuples. So Rishika is going to speak for about an hour, and then we are going to reserve about 20 minutes for questions at the end of the lecture. Please do type in your questions in the main chat box. We'll fill all the questions and ask Rishika D at the end of the lecture. All participants are requested to kindly keep yourself muted throughout the lecture unless asked by the speaker. Now, without any further delay, let us begin today's talk. Over to you, Rishika D.
Thank you. Good afternoon, everyone. So our topic is Gallagher, Sieve, and Diophantine M tuples. So this is the first talk in the session of two talks in the series of two talks. Today we'll see mainly what is Gallagher sieve and look at the background of sieve theory, and then move on to look at the problem of Diophantine M tuples and use Gallagher's sieve to solve the problem. Okay, so let's start. So okay, we'll start with the background of sieve theory. So sieve theory is a set of general techniques in number theory for estimating the size of sets. Sieve theory had a very slow beginning in the starting. The initial sieves we had were like Broom sieve and Selberg sieve, but they were very technical for somebody to understand. It was Ivaniak who made the thing simpler and made it reachable to most of us. Okay, so it was developed in an urge of proving ancient conjectures like the Goldbach conjecture, and the twin prime conjecture. These conjectures have not been resolved, but we have succeeded in proving various powerful results relating to them, like the Brunn's theorem, which states that the reciprocals of the twin prime converges, while we all know that the reciprocal of prime diverges. So Brunn's theorem was one of the first achievements of sieve theory. Second major achievement was the Chen's theorem. So the Chen's theorem is a very powerful and a beautiful result. So the Chen's theorem states that there are infinitely many primes p such that p plus 2 is either prime or a semi-prime. So semi-prime means a number having having two primes in its prime factorization. Similar theorem of Chen states that every sufficiently large even number can be written as a sum of prime and a prime or a semi-prime. So both these theorem of Chen are considered as a near miss of Goldbach and the twin prime conjecture. So this problem of unable to differentiating between primes and semi-primes is also known as the parity problem. So the parity problem is one of the biggest problems that sieve theory is battling on. The bounds that sieve theory gives are either twice the bounds required or are sometimes too overestimated because of this problem. The general sieves are unable to differentiate between numbers with odd prime factors and even prime factors. Okay, moving further. Now we'll look at the general setting in which we'll use the sieve techniques. So we are given a set A of objects for the sake of number theory, generally natural numbers, and a set of primes P such that we associate a subset AP of A with each P in P. And then we want to estimate, so the sieve problem is to estimate the sieve function, which is defined as SAP, which is equal to A minus union of AP over all P in P. Okay, so looking at this, if anybody can tell us how can we give a bound on the sieve problem. Okay, so this can be easily solved using the inclusion-exclusion principle. But the problem that we face in using the inclusion-exclusion principle is what we really need is all the primes that are in P, which is again a problem that we don't know what all primes do we have less than a number, or we have very less information relating to the set of primes. And using this inclusion-exclusion principle is like a never-ending process and is very complicated to do. So even if we want to state it, we can consider a set I subset of P such that AI is the intersection of all APs, P belonging to I, and A phi is A. Then the size of the Sieve problem, that is size of SAP, is equals to summation over all I subset of P minus 1 to the power size of I into size of AI. So this is the basic Sieve problem setting. If anyone has any doubts still here, they can speak. You are welcome to ask doubts anywhere between the presentation. I would love to answer them. Okay, in that case, moving further, so for the sake of number theory, we generally take AP as a set consisting of elements of certain specified congruence classes modulo P. Because what we really want to project is trying to study the image of a set modulo P, studying its properties, and then projecting it back to set A to study the properties of A. Now we'll consider a simple example just to understand this setting. So consider A. A is the set of all natural numbers less than x, and P is the set of all primes less than z. Generally, z is taken as some function of x like log x, x to the power 1 by 2, delta times some function of x. Whatever we need, it depends on the way we need the bound. Okay, so if we evaluate here SAP, the size of SAP, we'll get an upper bound on primes less than x. The upper bound, because we can take z to be less than x, we can take z to be 4, 3, or maybe just 2. So that will just give an upper bound on primes. If we take z to be x, we'll get explicitly the number of primes. Even if we take z to be x to the power 1 by 2, it will give us exactly the number of primes that are less than x. And this is what is known as the sieve of Eratosthenes. So now this is it for the general sieve theory. Next, we'll move on to the Gallagher sieve, and before looking at the Gallagher sieve, we'll see to a function known as the von Mangold function. So von Mangold function is an arithmetic function, is a very important arithmetic function in number theory. Any book on analytic number theory, you'll see this function occurring many times. So most of the arithmetic functions, as we know, are either additive, multiplicative, completely additive, completely multiplicative, or have some nice properties out of these. And having these properties is the key to understand such functions. But von Mangold function is neither additive nor multiplicative. It is defined as log p if n is some power of p and 0 in all other cases. So one very basic summation identity related to this function is summation of lambda d divides n is log n. You can observe this clearly as for only the prime powers, this is log p. So the number of prime powers that are in d, it will be log p that many times. And for all other cases, it is 0. So we'll just multiply exactly all the prime powers once, and this will give us log n. So this is the basic identity related to lambda of d, and this is used to write an explicit expression of lambda using the Mobius inversion, another beautiful property in analytic number theory. Okay, so just to signify this importance of this function, I would like to state that this function played a very important role in the first proof of prime number theorem. What it was mainly considered was the summation of lambda p for all p less than x, and it was something known as the Chebyshev's function, and studying the properties of that further, it was what that led to the proof of the prime number theorem. The Selberg's proof for prime number theorem, that is a very elementary proof of prime number theorem, also depends on this function, von Mangold function. Okay, so now we'll see the approach of the Gallagher sieve. It is a bit different from the general sieves. So we consider set B as a finite set of natural numbers and T as a set of prime powers. Okay, so our Gallagher sieve is also known as the larger sieve. Larger sieve because we already had something known as large sieve, and the large sieve dealt with the set of primes, and here we are dealing with the set of prime powers. So the problem in the large sieve is basically the same except for considering primes rather than prime powers. So it considers more things to estimate the set B, so it was named as the larger sieve. Okay, so what we know is an upper bound on the image of B mod T. Like what I said, we know something about the image of the set modulo prime powers, and using this the properties of that image, we want to project that back to the original set and see the property of that set. Okay, so we are given an upper bound on B mod T, and using this, we want to estimate the size of T. This is the basic problem of Gallagher's sieve that we want to consider. Okay, so under this problem, the theorem we have that given a set B of natural numbers and a set T of prime powers, we define X as the maximum of the set B, and the upper bound that we are stating it explicitly as the size of B mod T is less than or equals to UT. UT is some function in terms of T. So given that the denominator summation T belong to T lambda T over UT minus log X is greater than 0, we know the bound that the size of P is less than or equal to summation T belonging to T lambda T minus log X over summation T belonging to T lambda T over UT minus log X. So this bound uses the von Mengor function, and it considers von Mengor function because we want to consider all the prime powers, and this is one important function that has some value for a prime power and is 0 for all other cases. So in all the problems related to sieves, in all of the sieves as well, what we want to consider is like we have some function, or we build some arithmetic function which is either 1 or has some specific value or is greater than some specific value for the primes or the prime powers, whatever we want to deal with in that case, and is 0 in all other cases. So we kind of want an indicator function to signify if something is a prime power, is a prime or not. Not exactly an indicator function, but somewhat in that way. Okay, so next we'll see the outline of this proof of this theorem. I have tried to take all the details, but there are a few that I've missed. From here, the proof may look a little intimidating, but it is good. Just try to look at it and understand it. Okay, so given a T belonging to T, we define Z B comma T comma R for each residue class R mod T as the size of B such that B is congruent to R mod T. So under this definition of Z, we write size of B as the summation of Z B comma T comma R over R mod T. Now, using this equality here, we square this equality, so we square this equality here and get that size of B whole square is equal to summation of Z B T comma R over R mod T whole square. And now using the Cauchy-Schwarz inequality, I think you all must have seen specifically in terms of vectors, and this is an easier version of that. Okay, so the Cauchy-Schwarz inequality is summation AI BI whole squared is less than equal to summation of AI squared into summation of BI squared. Okay. And we are given that size of B mod T is less than equals to UT. And using both these things, we write that the size of B whole squared is less than equal to UT times summation of Z B comma T comma R whole squared over R mod T. Okay. So next we'll consider, we'll just take this U of T to the left hand side and write it as size of b whole squared over ut is less than equal to size of z b comma t comma r whole squared over r mod t, summation over r mod t. Now we know that the size of b is what we want to estimate and u of t is what we know. So using u of t, we want to estimate size of b. So what is something that we want to remove from this equation is the right hand side, that is summation over r mod t z b comma t comma r whole square. So next we'll try to estimate this thing on the right side, that is z b comma t comma r whole square summation over r mod t. Okay, so summation of z b comma t comma r whole squared over r mod t, this can be written as, okay, so before stating this equality, I would like to repeat the definition of z. So z b comma t comma r is defined as the size of the set b belonging to b such that b is congruent to r mod t. So just writing the statement in terms of indicator function and summating it over r mod t, we write summation of over r mod t, summation b belonging to b be congruent to r mod t 1 whole squared. And then just trying to write this square in terms of b and b prime, summation over r mod t multiplied by summation b belonging to t, b belonging to b be congruent to r mod t 1 multiplied by summation b prime belong to b, b prime congruent to r mod t into 1. Now again trying to pair it up. Okay, so one important theme in analytic number theory, maybe I should say, is to play with summations, and that is what we are doing. So interchanging summations, taking one out, putting one another, is what brings many results. One other technique that we used is a partial summation, if some of you are aware of. If not, it's completely okay. I was just trying to mention it. Okay, so back to our problem. Summation over r mod t, summation b comma b prime belongs to b, and b and b prime both are congruent to r mod t into 1. Now here b and b prime can be either same or different. So just trying to separate two of these cases, we write summation r mod t, summation b belonging to b be congruent to r mod t plus summation b comma b prime belong to b be not equals to b prime b comma b prime is congruent to r mod t into 1. So this term is where we are considering b equals to b prime, and this is clearly the one that where we are considering b not equals to b prime. What remains constant is that b is congruent to r mod t, so it is b comma b prime is congruent to r mod t, but given b and b prime are the same, this condition is enough that b belong to b is congruent to r mod t, and when not equals, we have considered b and b prime both as r mod t. So observe this first set is the same here, and this was nothing other than z b comma t comma r. So this part where b and b prime are equal yields again summation r mod t z b comma t comma r. And we know summation z comma b comma t comma r is the size of b. So again, we have reduced the number of variables that we had and reached to what we wanted to estimate. Now for the second term, we can write as b comma b prime belongs to b not equals to b prime, and this last condition can be written as t divides the difference of b and b prime. So just see the equivalence of these two sets, that b comma b prime is congruent to r mod t and t divides b minus b prime. So just exchanging that. Now what our next step would be, we'll multiply this to our von Mingold function. Von Mingold function is log p when n is a power of prime, and in all other cases it is 0. So it is somewhere signifies primes and it somewhere signifies the primes and the prime powers. If you try to look at it in a way, like summation of log p less than equals to x, it will somewhere give us a LCM of all the numbers, largest common multiple of all the numbers less than x. Because we have considered all the prime powers, and that is what we consider in the LCM. So this von Mengol function is a very interesting function. Okay, so using this what we have achieved here, that summation r mod t of z b comma t comma r whole squared is equal to the size of b plus summation b comma b prime belongs to b not equals to b prime, and summation t divides b minus b prime into 1. Multiplying this by von Mengol function and summing it over for all t belong to t. So summation t belongs to t, size of, here we had size of b whole squared over ut, so size of b whole squared over ut multiplied by the von Mengol function, and then summation for t belong to t. So similarly on the right side, this is less than equal to summation of b into lambda t, summation over t belong to t, but because the size of b does not depend on t, we can pull that out. Then adding to that, we would have the second term, summation b comma b prime belongs to b not equals to b prime, summation t divides b minus b prime into lambda of t, and then summation t belongs to t. So here we have again interchanged the summations. We had taken the summation over t afterwards, but we have pulled the summation of b comma b prime belongs to b outside summation t belong to t. So this can be done until the summations are independent, and sometimes we change the variables and trying to interchange the summations. So yeah, okay. So now the first inequality looks more or less like what we want to achieve. We wanted to okay. Looking back at the theorem, we had von Mengol function in our theorem. We had size of b. So we also had u of t. So what we really want to get rid of is, is the second term. Okay, so now we'll try to estimate the second term. So summation b comma b prime belongs to b not equals to b prime, summation t belongs to t, summation t divides b minus b prime, lambda of t, this is less than or equal to summation b comma b prime belongs to b not equals to b prime, and we have written this as log of b minus b prime. Okay, so I would like to ask how have we changed this into log of b minus b prime? Okay, so it is from the very elementary inequality that we have learned about lambda. Looking at it again, yeah. So we had summation of lambda d divides n is equals to log n, and what we have there is summation t divides b minus b prime lambda of t. So clearly this should be log of b minus b prime. Okay. So we have log of b minus b prime, but what I don't understand is this, why we have put this in inequality? Why not an equality here? Okay, so this is because the summation is only over those t's that belongs to t. Maybe some of the divisors of b minus b prime does not belong to t. So that's why we have this inequality here, because we have added some of the extra divisors of b minus b prime. Okay, so this is less than equal to log of x, because x was the highest term, was the greatest term in the set of b. So this log of b minus b prime has to be less than log of x. And because all the b and b prime are natural numbers, so this has to be positive. If it was allowed for b prime to be negative, then it would have been log of 2x. Okay, so this is less than equal to log of x, And because this log of x now does not depend on b and b prime, we can pull that out and write this as this is less than equal to log of x summation b comma b prime belongs to b not equals to b prime into 1. Now, what is this inequality here? So if you remember, we had reached to the same inequality here. Yeah, so this was this inequality, this was b square, and this is size of b square minus size of b. I would say a similar inequality rather than the same. Okay, so this is equals to log of x size of b whole squared minus size of b. Because we are considering not only only the cases when b is not equals to b prime, so we are subtracting the cases where b equals to b prime. Okay, and the size of size of b whole squared, because we are considering b and b prime belongs to b. So this is size of b whole squared, and the second condition that b not equals to b prime implies that size of b minus size of b square minus size of b shall be there. Okay, so after this, just putting this what we have received here through trying to estimate this term, we'll again put it into our original equation, and we'll get summation t belong to t size of b whole squared lambda t over ut is less than equal to size of b summation t belonging to t lambda t plus just replacing this by this estimate that we have received, that is log x multiplied by size of b whole squared minus size of b. One other thing that we need to notice here is that all the inequalities should be such that they satisfy each other, that we can carry out the sequence of operations, sequence of estimations, and finally use them. Okay, so so as we can see, every term has size of b common in them. So we can cancel that size of b from every term, and that would give us summation t belonging to t size of b into lambda t over ut, and this is less than equal to summation t belonging to t lambda t plus log of x into size of b minus 1, because this was size of b whole squared minus size of b. So taking out size of b common, this would be left as size of b minus size of 1. Okay, now just trying to shift the terms which have size of b common, pulling them to the left and all other terms to the right. We have size of b into summation t belong to t lambda t over ut minus this log x is less than equal to summation t belong to t lambda t minus log x this log. Okay, so now just put having size of b on the left side and bringing this to the right side, we will get size of b is less than equal to summation t belonging to t lambda t minus log x over summation t belonging to t lambda t over ut minus log x. Okay, so this was the expression that we wanted to prove. Yeah. Okay, so where have we used this condition? Looking at the proof again, have we used this condition? Okay, so we have used this condition in this step when we are bringing this to the right. If we don't have the condition that this is greater than 0, the inequality here would invert. Okay. Okay, so this is it for the proof of Gallagher sieve. If anybody has any questions till now, shall please ask. If not, we'll move further. Now we'll try to look at an example. The example is a very vague one just to see how can we use this Gallagher sieve. Okay, so what we'll try to estimate is the size of even numbers. So we all know even numbers are the numbers that are divisible by 2, and number of even numbers less than x is the greatest integer of x over 2. So this sign is of greatest integer. So we are all aware of the size of the set. So we are just trying to estimate this set so that we can check if our sieve is working correctly or not. Okay. So we'll try to estimate the size of even numbers. So what we can take as the size of what can we take as the set B? Clearly even numbers, because that is what we want to estimate. So B is the set of all even numbers less than x, and what we are considering as T is the set of all odd primes. We are not considering all the primes because what set T we need to consider depends on the problem that we are looking at. What primes do we need in the problem? Maybe I wanted to see the size of even numbers and the size of all the numbers that are divisible by 3. So then I would miss 2 and 3 and start from primes 5, starting from primes equal to 5 to z. So similarly, if I wanted something else as my estimating set, I would change my t accordingly. So here, because I want to consider even b's, I have considered all primes other than 2. So clearly this will give an upper bound because there would be some primes between z and x, which would give me something which can give me numbers that that would remain in B, that would not get sieved out by T. Okay, so a possible upper bound. So as we know, what conditions we need to use Gallagher's sieve was that we are given B as a finite set of natural numbers that we have as even numbers. We have also considered T as the set of odd primes. Now we also need to have an upper bound on the image of B mod T. Okay, so for that, what would be the upper bound? So this would be the most vague upper bound mod T of any set, that is T. Maybe T minus 1 would be a better one, but just to make things a little easier, I have written it as T, because what we just want to see is the conditions that we need and how to apply the sieve. So again, I would like to mention here, all the sieve theory methods heavily depend on the way you are estimating your sets. The estimations should be like the best that we can have to get better bounds. I think this would be more clear at the end of this example. Now okay, so what is pi z here? Pi of x is a prime counting function, that is number of primes less than x. Pi of x would be equal to the number of primes less than x. So summation t belong to t lambda of t is less than or equal to pi z into log z. Okay, so how I have considered this bound, this is like very clear one. So lambda of t is log p or 0. So in both the cases, log p or 0 are less than log z because we are considering the primes that are less than z. So not, I'll remove this summation, yeah. So lambda of t is less than log z, and then when we summate over all the t in t, we multiply it by the number of primes that we have. Because we have removed 2, we are just considering odd primes, we can again consider this as pi z minus 1. So it would be a nice exercise for those who are interested to try to do this again with better bounds. Maybe just just including these -1 here, -1 here can make things a little better. Though I don't say that they will, but they may. So now, uh, we have got an lower bound on lambda of t. Okay, so why we need these bounds? To look at these, we can look at the theorem again. Okay, so what we really need is we want this some inequality in this form. So we want an upper bound for the numerator and a lower bound for the denominator. So an upper bound of the numerator is what we have received, that is pi z log z minus log x. And for the lower, find a lower bound in the denominator, we have clearly lambda of t has to be greater than equals to log 3 whenever t is a prime power. Whenever t is a prime power. And we are just multiplying log 3 by the number of primes that we have less than z. So the zeros are neither counted on the right hand side or on the left hand side. So we can use this inequality that lambda of t not equals to 0. Given that lambda of t is not equals to 0, lambda of t is greater than or equals to log 3. And then multiplying it by pi z. Okay, and then finding a lower bound on u of t, it would be z minus 1. Like a possible upper bound on size of b mod t is t. I've written here t, or as I mentioned, it can be t minus 1. So here what I've used is t minus 1. So summation t belong to t, lambda t over ut is greater than equals to pi z into log 3 over z minus 1. These values in our statement, that is size of b is less than equal to summation t belong to t lambda t minus log x over summation t belong to t lambda t over ut minus log x. So as I said, we'll replace this by pi z log z and this by pi z log 3 over z minus 1. Okay, now the people who know a bit about prime counting function, okay, before talking about prime counting function, we'll take z as root x. We can take smaller bounds on z or larger bounds. We can take z to be log x. We can take z to be x to the power 1 by 3. So it depends on which way you want to squeeze your inequality to, which way you want to move your inequality to, and what would be the ambient conditions. So it would require a lot of analysis to see what value of z will provide us the most ambient results. But here I've again put the same as what we use in the sieve of Aristosthenes, that is root of x. And just using that, we'll get size of b is less than equals to half times pi x to the power 1 by 2 into log x minus log x over pi x to the power 1 by 2 log x log 3 over x to the power 1 by 2 minus 1 into log x. Sorry, minus log x. Okay, so now for the people who know the prime counting function shall be knowing the fact that pi of x is less than 2 times x over log x. Sorry. Yeah, so 2 times x over log x. Okay, sorry. Everywhere, wherever I'm using this law, it is mostly in it is natural form. Okay, so, that does not, okay, I'll make it clear. The using the whatever base we will use, that will not affect a lot here, because we are just taking a constant base, whatever you want to take, like just take it and move with that. This will just change this constant here if this is base e or base 10. So the constant would change, nothing else. So you can take it to be log x or whatever you want to consider. And this would be greater than log 2 times x over log x. So why we need both side bounds? Because for the numerator, we will need an upper bound, and for the denominator, I'll need a lower bound. Okay, so just putting these bounds in and changing root of x minus 1 to root x to make our calculations easier, we'll get that size of b is less than equals to 2 times root x log x minus log x whole squared over 2 log 3 minus log x whole squared. To illustrate a bit how we'll reach to this is by just we'll change this here to over log x, so log x will cancel, but in this we again get a log x in the denominator, and multiplying by that we'll have such kind of a expression. Okay, maybe there are small mistakes in the calculations that can be looked at, but what was the aim to present this example was just to make you feel how can we use the Gallagher sieve. So also from this example, I wanted to highlight, though we have a very good sieve method, but still what we'll need is these upper and lower bounds on some nice arithmetic functions to really use these sieves. And a lot of energy in using these sieves, or a lot of complexity in using the sieves after we have a sieve available, like we have Broom sieve now, I just want to use it. Or I have this Gallagher sieve as we have done and I just want to use it. So I would need a lower and upper bound, and deriving these lower and upper bounds is what needs a lot of work, because these bounds have to be good, have to work in the direction we want, and a lot of ifs and buts, a lot of analysis goes into this. Okay, so I would like to ask, if we look at this roughly, it looks like this is capital O of x over log x, root x over log x. But as we saw in the beginning, or we all know, that the size of even numbers is of the order x by 2. Okay, so what about order? Order means that size of b is less than equals to some constant times the function that is inside this bracket. So that is what is also known as the capital O notation, if you guys are aware of, or otherwise you can just take it this way, that size of, from this sieve, what we have received is size of b is less than equals to a constant times root x over log x. And this is clearly wrong, because it has to be x by 2. So if someone can point out where have we done the mistake. Okay, so I'll just switch to the slide where the theorem was, and if you guys want to revisit that and then would like to answer the question. Okay, so the theorem is, if this denominator is greater than 0, size of p is less than equal to summation t belong to t, lambda t minus log x over summation t belong to t, lambda t over ut minus log x. Okay, so it is clear that what the mistake that we have done is we have not checked the condition that the denominator has to be greater than 0, and we'll observe that 2 log t log 3 minus log x whole squared is clearly less than 0, because 2 log 3 is a constant and log x is an increasing function. Maybe this bound would hold true only for the cases where log x is less than 2 log 3. Log x whole square is less than 2 log 3. For all other cases, this bound would not work. And as we saw in the proof, again, looking at the proof, this step where we are switching from right to left, we are switching this denominator. We are bringing this denominator to the right. And if this denominator is negative, the inequality will change. So as we know the denominator is negative, what we can rather say is that the size of b is greater than. So rather than an upper bound, what we have received is a lower bound, that the size of b is greater than equal to 2 root x log x minus log x whole square over 2 log 3 minus log x whole square. And this holds true because this is of the order root x over log x, and root x over log x is finally less than x over 2. I mean, after sufficiently many steps, it is less than x over 2. So what we have proved, now we can see it is correct. Okay, so this was the example. I hope it is illustrated how can we use the sieve, and also illustrated that having a sieve is not enough to find a bound on a set. What we also need is bound on specific function, having those specific functions and knowing what function should I use, what value of z shall we take, what t shall we take, and a lot of it depends on a lot of the bounds that we want to derive. The quality of our bounds depend on all these things a lot. Okay, so this is it for today. Today we have discussed the basics of sieve theory, and then just had a glance of von Mangold function and used that in Gallagher's sieve, and just try to see to a vague example of Gallagher's sieve. There are a lot of easy examples that you can try and check if Gallagher's sieve provides really some good bounds on your set. But broadly speaking, there are a very few places where we can't really use Gallagher's sieve. The reason lies in the fact that the Gallagher sieve loses a lot of information. You have to have B mod T for every prime. If you don't have, then your bound would be very, very bad. And the information should be good enough to have a good bound. So in most of the cases, other sieves provide better bounds. There are really a very less number of problems that really use Gallagher's sieve to derive something good, because here we used for even numbers and we were not successful. Maybe okay, so I will not say that we cannot derive the size of even numbers, because the bounds that we have used here are very crude, very crude. Maybe if we had used better bounds, we could have found this result. But whatever, what I just wanted to say, there are very few places where Gallagher's sieve found real life applications, though it is a very basic and a very beautiful sieve. Okay, so in our next talk, what we'll see is the problem of Diophantine M tuples and how beautifully it uses Gallagher's sieve to derive its bounds. Thank you everybody for listening so patiently. If anyone has any doubts, can please discuss. Also, if you have any doubts left from today's presentation, you can ask them tomorrow as well. Okay, so for any doubts for now?
Thank you, Rishidari. That was a really nice talk.